All right, welcome everyone. So in this video, we are going to prove a theorem about the relation between row, column, null spaces of the matrix A and A transpose. And so we worked through a specific example where we identified that for a given m by n matrix A, that if we find the row space of A, or basis for the row space of A, and we find the basis for the null space of A, that we can show that these two spaces we saw that they were orthogonal complements to each other. And similarly, we looked at the null space of A transpose, and we identified that in that specific case, that happened to be the orthogonal complement to the column space of the original matrix A. So this is a result which is true in general, namely for any m by n matrix A, the orthogonal complement of the row space of A is the null space of A. And the orthogonal complement of the column space of matrix A is the null space of A transpose. So let's show why this is true in the general case. So let's consider a vector x, which is in the orthogonal complement to the row space of A. So that means if I take matrix A and I multiply it by vector x, then matrix A we can write as row vector 1, row vector 2, all the way down to row vector m. And now if we know that vector x is in the orthogonal complement to the row space of matrix A, well, if I were to take the product of A and x, then I can write this as row 1 dot product with x, row 2 dot product with s. Because if I were to take this product, I would take each of the entries in row 2 and multiply them by each of the entries in this vector and then add them all up. So this product of A times x I can write as row 1 inner product with x, row 2 inner product with x, all the way down to the last row, which would be row m inner product with x. And because x is in the row space, or in the orthogonal complement to the row space of A, this tells me that x should be orthogonal to every row vector of matrix A. So that tells me each of these dot products, if x is orthogonal to all of these row vectors, that when I take their inner product, I should get a whole vector of zeros. So therefore, we see that if A times x equals the zero vector, then by definition, this vector x is in the null space of matrix A. So this tells me that any vector x that's in the orthogonal complement to the row space of A, that has to be in the null space of A. And if I want to show that these two sets are equal to each other, namely that the orthogonal complement to the row space of matrix A is equal to the null space of matrix A, then we also need to show that for any vector that's in the null space of matrix A, that vector also has to be in the orthogonal complement to the row space of matrix A. And so going in this other direction follows very similar to the direction we just showed. So now we start with the vector x in the null space of matrix A. And by definition, if it's in the null space of matrix A, then I know that A times x gives us the zero vector. And this therefore tells us that vector x is actually in the orthogonal complement to the row space of A. Since I know A times x is equal to row vector 1 dotted with x, row vector 2 dotted with x, all the way down to row vector m dotted with x. And I know that ax equals 0. So this tells us, therefore, that each of these dot products should equal 0, has to equal 0, and that, therefore, x has to be in the orthogonal complement to the row space of A. So now I showed any vector in the null space of A has to be in the orthogonal complement to the row space of A, and vice versa, that any x which is in the orthogonal complement to the row space of A, that this vector has to be in the null space of A. So therefore, these two sets are equal to each other, and the orthogonal complement to the row space of A is equal to the null space of A. And you can prove very, very similar to the proof that we just did, that the orthogonal complement to the column space of A is equal to the null space of A transpose. I'll leave that part of the proof for you to work out.